Good morning children, welcome back to my channel. In the last class we have discussed about composition of functions, invertible functions and how to solve problems on composition of functions and invertible functions. In this class I have come with a new topic under your lesson relations and functions. The topic is, as I have written here, binary operation. So let me define it. So the definition goes this way. A binary operation star on a set A is a function star from A cross A to A. We denote star on your ordered pair AB by A star B. So the new term which we are learning here is binary operation. So what is a binary operation? A binary operation star on a set A is a function star from A cross A to A. That means children, on my set A, if I take the Cartesian product of a set A, which is A cross A, as my domain, then what it says is that under this function, if you apply one definition on this set A cross A, the final outcome answer will be in your set A. Okay, if this condition is true, then your function star is said to be a binary operation. And how do we denote it as? A operation star, or your binary operation star operating on elements A and B in the ordered pair is given by A star B. It is read as A star B, or it is read as A binary operation over B. So let us solve some examples to find out whether a given function is an binary operation or not. Ideally the symbol star is generally recognized as a binary operation. You can also have other notation, but you have to check whether it's a binary operation, or in the question it should be given that it is a binary operation. Okay, so star is always a binary operation or not, you have to check it. Okay, it may just be a notation also. Okay, so I'm going to take my set on Z plus. This is my set A. Okay, I'm going to define my star. Okay, I am going to define my function star by A. Now I'm just calling here function star because I don't know whether it's a binary operation or not. So this function star as A star B is equal to A minus B. Okay children, now since it is Z plus, this set will contain only positive integers, not even 0 also, right? So the idea in my mind first will come is, then what will happen if my answer is negative integer? It can happen, no? If I take two elements from my A cross A, the final answer can be negative. Let us check, will it happen? Suppose if I take my A as 3 children and if I take my B as 4, under this definition it will be 3 star 4. So answer will be 3 minus 4, which is equal to minus 1, which violates the definition of Z plus, because Z plus. How is my star here children? Star here is from Z plus cross Z plus to Z plus, but in this star, the function is defined as A minus B and the final outcome comes out to be out of Z plus. So what happens here? Here just star is a function, but it is not a binary operation. Okay, very simple to check the definition, right? Now let me go for the second one. Now I am going to take my real number set. Okay, real number set. I am going to define my star as A star B is equal to AB square. So here I can see that product of real numbers are taken. Okay, where star is going from? Star is a function from R cross R to R. Okay, so how is my A star B defined as? A star B is defined as AB square. That means product of real numbers. Yes, you know that A is coming from R, B is coming from R. So product of two real numbers will be real number. Also B is coming from real number. So B square will also be a real number. So what will happen? The product will be in real number. So what you got? Final answer is in real number set. Therefore, now what will happen? Your star on real number under this function will be a, under this definition of function will be a binary operation. Alright children. Now let's go to the third example. Again, I am taking an example on Z plus. Okay, on Z plus, I am going to define, say, some operation. This one, inverted VOM, right? Okay, by define star this one. Okay, the operation this one by, say, A star B is equal to modulus of A minus B. Z plus, as I have seen earlier, here also it was Z plus, and in that example it made me remind of negative numbers, right? Now here children, when I look at the definition, I am very sure that because it's a modulus function, all the final answer whatever will be coming after taking elements from Z plus cross Z plus, the answer will always be positive. Let us check. For example, if I take some A as 3 and if I take my B as 4, both are Z plus positive integers. So what will be by definition? It will be 3 star 4 is equal to modulus of 3 minus 4, which is nothing but modulus of minus 1, that is going to be 1, and 1 is always in Z plus, right? So because modulus function has the property of making it always positive, I will have on this, okay, on this operation, my function is a binary operation under this definition. So your function, this function is a binary operation because my final answer is in a star plus. Is that clear, children? Okay. Now let us move to another topic. Okay, let us start with another topic. Now my another topic is nothing but operation table. Okay, it is an operation table. That means, suppose if I have a star from A cross, suppose if I have a star from A cross A to A, and my set A is containing all finite elements. Okay, then the operation table of star. So suppose if someone asks me to write the operation table of this star, then the operation table of star will contain n rows and n columns with the ijth entry ai star aj. Operation table. So suppose if I have a function star, okay, or let it be a binary operation, no problem. Now when I write like this, children, it is understood it is a binary operation because your A cross A is going to A. So it says that you can have an operation table, you can you are able to write an operation table for a binary operation only when your number of elements in the given set is finite. Then what will be operation table star containing? It will contain that much rows and that much columns depending upon the size of the number of elements of your set A, with the ijth entry given by A star ij. The ijth entry is given by ai star aj. Okay, let us write an example, children, then you will understand better because it doesn't it doesn't appear to be so obvious, right? So I am going to define one example. Suppose, children, if I have a set A, okay, 1, 2, 3, 4, 5, finite set, there are 5 elements. This is what it demands. You should have 5 to form an operation table. You should have finite number of elements. So say I have a set A 1, 2, 3, 4, 5, and I have a binary operation, say star from A cross A to A. Okay, now how is star defined as? A star B is defined as minimum of A comma B. And suppose I am asked to write an operation table for this. It's already given to be binary operation because A cross A is 2A. Or given any operation, after you are able to prove that it is a binary operation, you can very well draw the table for it. Or given any function, children, after writing the operation also, after checking the behavior of the elements in the operation table, you can check whether it's a binary operation or not. It is a two-way process. You can use it as for checking whether it's a binary operation, or whether if it is already given to be a binary operation, you can write the operation table for it. Both way it is, conversely and the forward part, both is true. If binary operation given, you can form an operation table. If operation table is given, you can check and find out whether the given function under that definition is a binary operation or not. Okay, so I have here 5 elements, so I have 5 rows and 5 columns, right? So it will be 1, because the elements are 1 2 3 4 5. I'll write here 1 2 3 4 5, 1 2 3 4 5. So these are all the possible combinations of the ordered pairs. Okay, so what will happen? How is it defined? A star B is defined as minimum of A comma B. So 1 1 minimum is 1, 1 2 minimum is 1, 1 3 minimum is 1, 1 4 minimum is 1, 1 and 5 minimum is 1, 2 1, 2 2, 2 3, 2 4, 2 5, 3 1, 3 2, 3 3, 3 4 minimum is 3, 3 5 minimum is 3, 4 1, 4 2, 4 3, 4 4, 4 5. Okay, 5 1, 5 2, 5 3, 5 4 and 5 5. Is that clear? So here you can see that, children, this is called as the operation table, and very well you can see that in my operation table, whatever final outcome I am getting, they are all answers 1 2 3 4 5, and which is your definition of your binary operation. So given a binary operation, you have formed an operation table. Given an operation table, you can check whether the given operation or the given function is a binary operation or not. I hope operation table is clear, and you can write operation table for any set containing finite elements. Okay, now this is not as important, but we will move to something more important, but this is in your syllabus, so I have just introduced it. Okay, let us go to some more important concept, that is properties of binary operation. So I am going to start with properties of binary operation. So very important is, first of all, it should be a binary operation, then only you can call it as, or then only you can use it for making use of its property. Okay, properties of binary operations, very simple properties. Okay, so for this, first of all, I should have a binary operation star going from, say, A cross, this is cross, okay, A cross A to A. Okay, so star is said to be, there are properties, so write the binary operation star is said to be commutative if A star B is same as B star A for every A and B coming from your set A. Right? What is it saying? That you take elements from your set A, and if you try to apply the definition under the given function, under the given operation, then A star B will be same as B star A for every AB belongs to A. That means you know that, children, A cross A elements will be of the type ordered pair, right? You are sure of that, right? So, but only thing is here is, if you change the position of the order of the elements, the answer should be the same. That is called as commutativity. Okay. Second one, again, your binary operation star is said to be associative. So see, these words are familiar to you, right? You have studied these words in your class 11, right? So for associativity, children, you should require 3 elements. So how it will be? A star B star C, same as A star B and then with C. Here star means it's a binary operation. This happens for every A, B, C coming from my set A. That means if you are taking first the binary operation of B and C, and then then applying it with A is same as first taking the function binary operation of A and B and then applying with C. That means 1, then 2 and 3 is same as 1 and 2 with 3. Okay, this is called as associative property. Now third one and fourth one is very, very important. Okay, third one is saying that you are given a binary operation, and if in that binary operation, I am writing in short form. If in that binary operation, children, there exists an element, small e belongs to your capital A, okay, such that A star E, for any other element A, if you use it under the definition, your A star E will be same as E star A is same as A, then E is called as identity element. Is called as the identity element, right, in your star operation, binary operation. Okay, so what are you getting here? It says that A star E, if you do, you get back the same element, same as E star A, you get back the same element. How should be this element E here, children? This element E should be working for all. Okay, this should be working. There exists an element E belongs to A. Now this E belongs to A will be for all A belongs to A. So I will just add here and write for all A belongs to A, because you in a given set you can have only one identity, right? And identity, you know that identities are always unique. So if there exists an element A belongs to A such that A star E is equal to E star A is equal to A, not for one A but for all A, this identity E is working, then E is called as the identity element and is the only one and only one. It is one and only one identity element in star. Okay, identity elements are unique. Now fourth one. Okay, fourth one says that if in your binary operation there exists an element E belongs to A, then an element small a is said to have an inverse small b such that A star B will be same as B star A will be same as E. What does that mean? For given a binary operation star, there exists an element. If in that binary operation there exists, condition is very important. You should have an identity element. E belongs to A. E means identity element. Then an A means what? This A is from your set A. Then an A belongs to A is said to have an inverse again B belongs to A such that A star B is equal to B star A is equal to E. That means if you take two elements and if you apply the binary operation, you will get back your identity element. And how is this identity element? This identity element we have seen here, it is unique for all A belongs to A. So that means only those elements when you combine with A, when you will get back E, those elements will be having inverse. Have you understood, children? What am I saying? Only those elements when you work with binary operation and you get back your identity element, then those two elements are said to be inverses of each other. Here A is said to be the inverse of B, B is said to be the inverse of A. You should, when you combine them under the binary operation, if you get your identity element which is already defined in your set, then it is said to have, or then that particular element is said to have inverse. So I am very clear that every element may not have inverses. Okay, so let us solve problems on commutativity, associativity and on property of identity, and if identity is existing, its inverse we can find. Okay, children. So let us solve some problems based on it. Okay, so let me take some example. So let me take one. Suppose star is a binary operation. Star be a, many times it is also written as BO. BO means it is a binary operation on the set Q of rational numbers as follows. Okay, suppose the first one is A star B is equal to A square plus B square. Okay, now children, under this operation. We are going to check whether it is commutative, associative, identity element is there. If identity element is there, what is the inverse? Okay, yeah, so we are going to check all the 4 properties of your binary operation. Okay, so let's start with commutativity. So I'm going to start with my first part. Okay, so first part is A star B. Now you know that children, star is going from, if you want I'll write here, star is going from Q cross Q to Q. Okay, Q cross Q means rational numbers. No, it is rational number set, and from here you have ordered pair, right? So here A star B is defined as A square plus B square, right? A square plus B square. So I'll write here A square plus B square. If you want, you can rearrange it as B square plus A square. So this is same as children B star A. Yes. So what will happen? This will become, star will become commutative. Okay, now associative. What is A star B star C? We have to compute, right? So what is this? Always compute once in the bracket. So B star C is what, children? By definition of A square, first term square plus second term square. So it is going to be A star B square plus C square. Right? Now next time how it will be? This term square plus second term, which is B square plus C square the whole square. Okay, I am not expanding it. The other part, RHS is A star B with C. So how it is? Let me open the first bracket. So it is A square plus B square star C. So again apply the definition of this. So it will be first term whole square plus second term square. So if I without opening only I can find out whether it's same or not, because power of A is square. Power of A here when after opening the bracket will be 4. So definitely these both will not be same. Therefore I can say star is not associative. Okay. Now third one is checking identity. If identity is there, then only inverse will be there. So by definition A star E should be same as E star A, right? Should give you back the same element. And this E should be existing, or this E should be unique for all A belongs to. That means this E you apply for any element coming from your set, that will be of the type, giving you back the same element. So here by definition what will you have? A square plus E square, which is equal to E square plus A square, which is equal to A. Is this possible, children? No, this is not possible. This may work for one or two cases, right? That means E will not be same in all the cases, because it is the set of rational numbers. So which is not possible in Q. It is not possible in Q. Okay. So not possible in Q. Why am I saying so confidently, children? If I take my A as 1, if I take my E as 0, what will happen, children? 1 square plus 0, 1 square plus 0 square is 1, and A is again 1, so it is true. But will 3 square plus 0 square give you 3? No, 3 square plus 0 square will be 9. It will not be your 3. That's why it is not possible in Q. Therefore, it has no identity element. What has no identity element? It means here binary operation has no identity element. Therefore, you need not find what is the inverse. Okay. Let's go for the second one. Let us take A star B as A plus AB. Okay, so what is A star B? A star B, by definition, it is rationals. Okay, A plus AB. B star A is first term plus the product of first and 2. Are they same? No. So it is not commutative, because A star B is not same as B star A. Okay. Next one is associative. A star B star C is what? A star B plus BC. First element plus product of the next one. So next one, next again if I apply it here, how it will be? It will be A plus A into B plus BC. Yes or no? Right? First, what will I do? First B star C is what? B plus BC. So the first element plus product of these two. So what it will be? It will be A plus AB plus ABC. Now what about the next part? A star B with C. So it is A plus AB with C. Next time it will be A plus AB plus C times A plus AB. So without opening only I can say they are different because 1, 2, 3, 4 terms, here only 3 terms. Therefore, star is not associative. Why it is not associative, children? Because A star B with C is not same as A star B then with C. Coming to the third one, identity element. A star E should be same as E star A should be same as A for all A belongs to A if there exists E. So by definition what it will be, children? A plus AE is equal to E plus AE should be equal to A. Is it true, children? Can this happen? Can this happen? No, this cannot happen, right? So what will happen? This will not happen. That's why it will not be having identity element. Okay, because again reason is it is in the set of rational numbers and this is not at all possible. Okay. It may be true for one case, as I showed you in the previous case of here. It may be true in one case, but we don't want we don't want so many identity. We want one unique identity. So this is not possible in Q. This is not possible in Q. Okay. So what will happen? Does not belong. It's not does not belong to. We can write like this, which is not possible in Q. Therefore, it means star is not having, under this definition, identity element. Right? See, children, from here only you can see A plus AE is equal to A and A will get cancelled. So A is equal to A will get cancelled. AE equal to 0. Right, so if I write A equal to 0, A will be 0 upon E, that is 0, right? That may not work for all the elements. Okay, that's why I've said it's not possible in Q. Okay, if you want, we can do another problems. Okay. Let me read for you. You know that always I take examples from your NCERT textbook, okay? So because these problems are standard and once you are thorough with it, you can be solving any kind of problem given to you. So I have written a problem ready-made here. Let star be a binary operation on natural number given by A star B is equal to HCF of A and B. Is star commutative, associative? Does there exist identity for this binary operation on natural numbers? Okay. So let us solve this, children. So we have already given, you know that properties can be applied only when it is a binary operation. So it's a binary operation star going from naturals n cross n to n. Okay. With A star B defined as HCF of A and B. So first one is commutativity. Commutativity means what? A star B is same as HCF of A comma B can be rewritten as HCF of B comma A. So this is same as B star A. Right? Therefore I can say star is commutative. Yes or no, children? Yes, because both are same. Second one is associativity. A star B star C. Solve the bracket. So this is A star HCF of B and C. Again, if I simplify, it is again HCF of. So this will be an answer that you are going to take HCF with A. So it is actually finding HCF of A, B and C. Yes. Now, similarly, A star B with C. Right? So, what it will be? It will be again HCF of A and B with C. In short, it is HCF of A, B and C, because its answer again will be in natural number and we are going to do with C. So it is equivalent to find HCF of all the three numbers. So again I can see that A star B star C is equal to A star B star C. So I can say that my binary operation star is associative. Is that clear? Now the third part of the question is commutative, associative. Does there exist identity? Does there? So it is clear that all the binary operations will not have identity, right? So I have A star E is equal to E star A is equal to A. That means HCF of A comma E should be same as HCF of E comma A is equal to A. Now forget about this center part. Okay. A comma E. Okay. HCF of A and E will be A. Will this happen, children? Will every E be same? Will every E be same? No. Suppose if I have an element 3 children. Okay. So what will you write E to get back 3? Yes. If I take anything, children, if I take 3 comma 1, what is the HCF? If I take 3 comma 1, the HCF is 1. Yes or no? I am not getting back my element A here, right? If I take 3 comma 12, what will be my HCF? If I take 3 comma 12, my HCF will be 3. So that means 12 is my identity element. If 12 is my identity element, will 2 comma 12 give me 2? Yes, 2 comma 12 will give me 2 comma 12 will give me 2. But if I take 16 comma 12, will I get the HCF as 2? Will I get the HCF as 16? No. So that means this condition is not true because our identity is going to change depending upon your given element. That means to get back the same element back, you have different identities for different elements. So that means this is not possible in your set of natural numbers. So that means there is no E belongs to N such that A star E is equal to E star A is equal to A. Therefore, star does not have... See, here the problem is that E is not unique. For different elements, you are able to get different values of E, which is violating the definition. Therefore, does not have identity in your set natural. I hope your concepts are getting clear. Okay? I think one more problem we can do. Last one and we'll stop for the day. It is, let A equal to N cross N and star be a binary operation on A defined by A comma B with binary operation with another ordered pair C comma D is defined as A plus C comma B plus D. Is that clear? Now it is N cross N. Now how is the set here, children? It is N... It is A cross A, right? It is A cross A. I will not write this way. I will write in short form. Otherwise, it will be too lengthy, right? So, it is A cross A to A. No, children? So, that means my A itself here is a Cartesian product with another Cartesian product. That's why my definition here is given between... In the previous cases, it was just A star B. But here, what happens is, here your A itself is a Cartesian product with another Cartesian product of the same type. Right? That means with another A, which is the same thing, right? So that's why here the elements will appear as A comma B star C comma D, whereas in other cases you used to have only one N, right? So you used to have A star B. Is that clear? So we have to check it is again commutative, associative and as identity for this set N cross N. So let us solve, we know the usual way. So let us solve A star, we have to start here A star, not A star B, sorry. A comma B star C comma D. So how it will be, children? It will be defined as, it is already given to you, right? A plus C, it is given to you. A plus C comma B plus D. If you want, children, I can rewrite it as C plus A comma D plus B. Just I'm just changing because all are basically natural numbers, no? So 3 plus 4, 4 plus 3 will be same. So I am given permission to change the order. So this can be rewritten as C comma D star A comma B, because this is C plus A and D plus B. So therefore I have my operation star as commutative, or star is commutative anyhow. Now we have to go for associative, right? So A comma B star C comma D with E and F. So let's solve the bracket. So it is A comma B star. What will happen inside, children? Inside it will be C plus C comma D plus F. Right? Again apply. If I apply it again, it will be how it was C plus C, D plus F. This time how it will be A plus C plus E comma B plus D plus F. Alright. Now we have to check with the other part. What is that? AB star CD with E and F. Solve the bracket, first bracket. A plus C, B plus D, star, comma, F. Yes. So again, you can do it in the same way. Yes. So how it will be appearing, children? A plus C plus C, B plus D plus F. So you can see that this part and this part are same. Therefore, star is associative. Okay. Now we have to check whether star is having identity element under the function of A, which is under the set A, which is n cross n. So let me start with A comma B star E1, E2. Now I have written here two E's, right? Why? Because my set is A cross A. So this should be same as E1 comma E2 with AB, and this should give me back AB. So what does this mean by definition? A plus E1, B plus E2, same as E1 plus A, E2 plus B is equal to A comma B. Compare the coefficients. A plus E1 is A, B plus E2 is B. So if I solve, E1 is 0. If I solve, E2 is 0. That means my element is of the type 0, 0. Okay, element is of the type 0, 0. And 0, 0 is not in n cross n because it is a natural number set. Therefore, I can say that star does not have identity element. Okay, children? So we were able to prove that this operation star is commutative, associative, but does not have identity element. So there is no point of finding inverses for those elements. Okay. So children, we have successfully completed the topic relations and functions. I have covered all the most important topics of that chapter. Not most important topics, I have covered all the topics of that chapter. Relations, type of relations, functions, type of functions, composition of functions, invertible functions, and the last topic was binary operations. Hope you have enjoyed studying with me. Next time we will start with a new lesson and come with new subtopics. Thank you, children.